have the first presentation. And we're going to have on technical feasibility of glass optical fibers for automotive Ethernet. And welcome, Mabud, for your presentation, and the floor is yours.
Thank you.
So, thank you.
Kirsten. So let me start. Thank you, Kirsten, and also just, I know people have mentioned it, after 20 months of sitting in front of Zoom, WebEx, and I know there are people in hybrid, virtual, who are going through that experience. So it's terrific that this conference has been able to bridge both of those. So even with the COVID rules, it's great to be here in person. This is my second time in Munich, second time in this building. So thank you for everybody who's helped organize this terrific event. So as Kristen said, the topic is technical feasibility of glass optical fibers and fiber cabling for automotive Ethernet. My name is Mabud Choudhury. I'm with OFS. My co-authors for these, who unfortunately aren't here, but they're here virtually, are John Abbott with Corning, John Earnhardt with OFS, and Masato Shiino with Furukawa Electric. So just in terms of what I'll go into a bit of an introduction. Obviously, I think as I see most of the demos, most of the talks, this is a room with copper electrical PHYs. That's sort of very much what's been in automotive. My personal background 10 years ago was working on some of those one-pair technologies. Glass optical fiber is new, so we'll do some introduction in that topic and get some of the terms that are consistent for everybody. Then sort of foundationally, while there's not history in the automotive, there's a lot of history with glass optical fiber links in enterprise and data center networks, and that foundation is important in terms of what we're looking to do in automotive. We'll also talk about some other harsh environments. Automotive is a very challenging environment in lots of ways, high temperature and harsh environments being part of it. But there's other areas where optical fiber has been used that in some ways is more harsh than automotive and can still be cost competitive for automotive type applications. Then I'll talk a little bit about technical feasibility within IEEE, so the 802.3CZ project, and I'll talk about that briefly. Just a quick slide that there's photonics happening in automotive, so it's already here in lots of ways, as lots of people in this room already know. Then a little bit besides IEEE and ISO and IEC in terms of some of the standardizations that's happening to make sure that optical fiber and glass optical fiber is in fact a reliable, technically feasible standard, and then some summary and future work. So, and again, not in most of these technical presentations, Doug did a great job of introducing Corning as, and I think legitimately, a glass innovation company, more than 100 years history. OFS, the company I work for, probably most of you don't know, the term is optical fiber systems. Our roots are actually AT&T, Bell System, Bell Labs, actually goes all the way back to Alexander Graham Bell. And then Furukawa is also a company rooted in the late 19th century, addressing Japanese automotive markets, but a global footprint. And OFS, in fact, is a part of Furukawa Electric. So for this talk, what we're talking about, what's relevant, so legacy is always good, but it can be not always good. But what's important is, can we get the right sort of solution for this market in dealing with industrialized coating for cabling for harsh environments, based on experience that we have in other areas of automotive. So 802.3 Ethernet, I think everybody here is quite familiar with. There's two active projects right now by IEEE 802.3 terminology. There's two task forces, the P802.3CY and the P802.3CZ. The numbering is sequential, so they have been approved right one after the other. One dealing with electrical copper beyond 10 gig, 25, 50, and 100 with 25 gig lanes, and the other CZ, which is the area I'll focus in on, looking at beyond 1 gig on the optical side. So it's actually got potentially a lot of PMDs there, 2.5, 5, 10, 25, 50, PHYs or physical media dependent applications, and for generally longer reach than what CY is looking at, which is more like 11 meters. The key here, one of the terms that I'll use, is VCSELs, which is a vertical cavity surface emitting laser. So until roughly a gig or so, LEDs do a good job and they're a good low-cost solution. But as you get to 1 gig and beyond, it's VCSELs that really have the advantage from both technical and economic feasibility perspective. The fiber type that I'll be talking about is a multimode fiber, and I've got a couple of slides introducing it. Specifically, it's the OM3 type that's designed to work with high-speed VCSELs, and OM3 fiber can be industrialized for automotive applications, and can be easily done that way. So in terms of the standards, we've had a lot of these conversations. I mentioned that my second trip in Munich, the first time Kirsten actually helped organize a meeting here in this building for us on the one-pair side. So I mentioned that I have the Bell system legacy. Most people maybe know or maybe not know that the patent for the twisted pair was Alexander Graham Bell. So my story is he invented phone 1, then he invented phone 2, and he had to connect the two, and he invented twisted pair. So it's been around for a long time. It's an amazing medium from that perspective, and that legacy is important. How do you maintain that and keep improving it? And so I think we've heard that hundreds of millions of ports have been sold on 100-base T1. But that same standards sort of ecosystem is working now on these standards to go beyond 1 gig and 10 gig, both on copper and fiber. They're both widely supported by the OEMs, by the tier 1, tier 2, and component suppliers. So both, we see, like this meeting is in person and virtual. We think copper and fiber can be hybrid also, that they can be complementary. It's not one necessarily replacing the other. So specifics on multimode fiber and OM3. So OM3, again, is a type or grade of fiber. Multimode fiber is a glass optical fiber. Multimode meaning that it's got multiple light paths or multiple modes, as opposed to single mode, which is one mode that's in there. In the case of OM3, it's specifically a laser-optimized multimode fiber. I'll describe that a little bit further in subsequent slides. But it was designed from the outset to work with VCSELs, with high-speed VCSELs. So that combination of a link is critical, both in terms of technical feasibility, reliability, and economic feasibility and cost effectiveness. It's that link cost that really matters, the harness cost that really matters. So OM3 is a 50-micron core, 125 micron cladding. It's a graded index fiber. The table below is just for reference. It shows all the standards, predominantly based on your basic effective modal bandwidth of the fiber is how you grade the fiber. So again, the other driver behind this are the VCSELs, the light source. And this is, there's multiple companies. This happens to be from II-VI, which is acquired Finisar and has been sort of a strong VCSEL provider in the data center space. You can see that over time, it used to be for sensing. It's moved further and further. And the volumes have gone up to where it's now billions sold. So the application that a lot of people are familiar with is if you have an iPhone, it's your Face ID, essentially. So that's driven by having larger wafer sizes. And so VCSELs, which, like a lot of technologies, there's a prediction that they're going to go away, have instead have been thriving. And that high volume has driven lower cost. And automotive is very challenging in terms of volumes, but consumer electronics, the mobile phone market, in some ways is even more challenging, both in cost and volumes. So that's where VCSELs are. This chart happens to end with 6-inch wafers. They're looking at 8-inch wafers now. That'll further drive those cost curves down. Again, for background, there's been a 20-year plus history on VCSELs in data centers and local area network type applications. And it's that combination of getting that multimode fiber specifically designed from the way the bandwidth is characterized, the way the launch condition is characterized. Years of work. I'll mention that one of my co-authors, John Abbott, was a principal in developing some of those. We have somebody here from Panduit, Rick Pimpinella, who's done a lot of leading work in making sure that these systems operate in unison, give you the best reliability, and give you the best economic cost structure also. So one of the things that's interesting about fiber is that just as the raw fiber, multimode fiber is actually relatively more expensive than single mode fiber. By the time you put a jacket on and connectorization on, and by the time you look at the total link cost, it's where multi-mode VCSEL links actually have the biggest advantage. And they've had that advantage over multiple generations. And I'll quickly reference Graham from the keynote mentioned that it's not just your data rates today. Your car may need data rates 10 years from now that none of us are really talking about. It's not beyond 10 gig. It's whatever that application is. And that's very much happened in the data centers where you've seen data rates from 1, 10, 25, 50. We're now dealing with 100 gig lanes, and we're talking about 1.6 terabytes in data centers over multiple lanes or pairs. So I think making sure that you've got a cabling infrastructure, a physical link that can sustain upgradability, or once you qualify it, it's one that can last multiple generations, is important. I know it's been brought up, it's important in standards that you have interoperability, backward compatibility, and standards is sort of conservative. It doesn't like fundamental step changes. So it is a big change, but making that change enables sort of a very cost-effective technical solution for automotive for multiple generations. Just again, a little bit about what I mentioned, that IEEE over that 20-year span has gone from all the way from 1 gig to 10 gig to now dealing with 50 gigabaud PAM4 lanes. So that's 100 gig lanes, essentially, that are going to be deployed commercially next year. So it's here. There's always a question of how far can it go. There's a sense that VCSEL multimodal links can support up to 200 gig links. So again, I know Max did a great presentation in terms of, well, how much data do you really need in a car? So the question isn't just today, what do you need 10 years from now? I think is sort of what's happened in the data center space. And again, every time we think we've got enough of a data rate, it seems like you need more. So just quickly shifting focus a little bit, fiber has been, it's not, most of what I presented was data center, enterprise, local area network applications. Fiber goes in lots of different markets, and the one on the upper left corner is fiber to the X or fiber to the home. So this is an area where you have to compete with coax, with twisted pair, with satellite, with 5G. There's a whole range of technologies in a relatively harsh environment with handling that has to be done, and you have to be cost competitive. Industrial has some of that application also. And then the two I'm going to talk about is some temperature sensing and aerospace as sort of, again, a foundation for what can be done in automotive. So one of sort of the highest temperature applications for fiber is in distributed temperature sensing, and this is in the oil and gas industry. So you can get up to 200 degrees C and have a very reliable, robust system, essentially. Kirsten and Steve Carlson did an excellent job in reviewing our presentations and gave us some great feedback. When you see some of these things, and I'll mention at Aerospace, the first thing that jumps to you is, well, that's a much more expensive fiber, that's a much more higher cost environment. And that's true, but it's really saying technically the foundation is there, and given the volumes associated with automotive, those costs can be competitive for the automotive market. So the other one I mentioned, again, is aerospace, and there's, again, a long history there. I probably should have checked on the European fighter jets since I'm in Germany, but these are US fighter jets. This was the initial applications. Again, very high performance systems, and it's also extended now to commercial planes. So Boeing, Airbus, they're utilizing fiber essentially in mission critical applications. Initially it was infotainment, but they've moved on to avionic type systems. And again, very rigorously tested, technically reliable in some, obviously, we'll all be flying, or many of us will be flying to go home, so you need for those systems to work properly. The requirements, again, overlap with automotive. It's high reliability and long life. It's a wider temperature range than we're looking at automotive. This is the commercial range. The military range is even higher. Tight bends, insulation stresses, crush and clamping stresses, flammability. So all of those are requirements to get qualified in that market. So just some quick brief sort of test results for a particular fiber, avionics fiber, that's minus 55C to 165C, basically showing that it passes those requirements. This is the thermal cycling for that same fiber, again, the same wide 55 to 165 range. And again, a series of mechanical tests, cyclic flex, compression, and tensile loading and bending that it has to rigorously pass to be qualified. This was actually Corning, specific Corning fiber that was tested to more automotive numbers at 105, showing that, again, with the right coating and jacket material, there's really no concerns or issues, that there's strong technical feasibility from that perspective. I mentioned the 802.3CZ project, and Cesar actually mentioned KD-POF, and I want to acknowledge Ruben Perez Aranda and Carlos Pardo, who've been doing a lot of leadership work here. So this is link testing. In this case, it's with a Corning fiber, and it's just to stretch the limits, it's at 205 meters is one of those results. And again, from the full temperature range, in this case going from -40 to 125 degrees C. In each of those frames, the top link is looking at the eye diagrams, so the high and low, basically oscilloscope measurements, and then the one below is the planned signal processing, some of the work that KD-POF and others have been doing to make sure that these things would work. So we fully expect no issues at 50 gig. Frankly, you can go to 100 gig on these fibers without any difficulty, and we're certainly doing that in the data center applications. And again, this is sort of that multiple vendors. This happens to be an OFS fiber that, again, would not be the specific one for automotive. We would design that for that market with those needs, with commercial needs, but it shows essentially a proxy of the technical feasibility of that fiber. Just quick mention that LiDAR is where photonics are already here in the automotive market. And again, it's a similar, initially the cost seemed very high, and it comes rapidly down based on the volumes that automotive affords, and also the volumes that things like 3D sensing affords for the ones that are VCSEL-based type solutions. So cost effectiveness is definitely part of what is available with these optical solutions. Just switching that from an ISO standards perspective, there's a lot of active work going there. This is specifically an ISO TC22, and under the bottom one there, SC32, it's looking at basically from the hardware perspective, basically the entire link there. That includes the optical fiber. The fiber is one pair, so it's a transmit and receive pair fiber. And so there are test methods that are being developed and testing that's being made specific for the automotive environment. Most of the previous fiber standards dealt largely with enterprise data center, outside plant, fiber to the X type applications, but now it's looking specifically more for fiber in the automotive environment. The specific work that's going on there is ISO 24251. This is looking at the optical harness, that piece of it essentially. So the connectors and the cabling that's associated with it, and looking at it up to 100 gigabit per second qualification. So it's not tied specifically to an IEEE application. It can be other applications also. But some of that initial companies are beginning to collect that data, define those standards to make sure that we have a technically feasible and robust standard. IEC is another group that's now looking actively and looking at optical fiber. So this is TC86. It's looking at the fiber itself, because again, the fiber, and it's also the wavelengths that are being considered for optical, the 802.3CZ application. We're looking at potentially 980 nanometer type applications. So making sure that those are qualified properly in these component standards that IEC develops, looking at the connector and looking at the light source, whether it's VCSELs, and even silicon photonics has been proposed as a light source for this automotive application. So just summarizing things, I think the way we're demonstrating technical feasibility of glass optical fiber and reliability is based on this 20-year plus foundation that's in the data centers. Automotive imposes, as everybody in this room very, definitely knows, a series of additional challenges and requirements, and for every one of us, we have to be careful and sensitive to those. But that foundation, along with the foundation of glass optical fiber being completely robust and reliable in environments like distributed temperature sensing and aerospace, says that it certainly is qualified technically. And also, technical feasibility can't exist without economic feasibility. Ultimately, it has to be commercially viable and successful. So that's there. And it's really the high volumes that are associated with 3D sensing. And future work is basically to keep working on the IEEE, ISO, IEC, and OEM-specific requirements to qualify these solutions. So thank you.
Thank you, Mabud, for the very interesting presentation. I have one question. You've presented, of course, now a lot of advantages and good reasons to look at this in more detail. So why do you think the car industry is hesitant, or what do you think needs to be overcome in order for this to be more adopted or sort of in the industry?
Kristen, you know me from my previous life as a Twisted Pair person, which is probably why you asked the question. So why does Twisted Pair stick around? Because Twisted Pair has been there since 1881. It's familiar. It's the industry's dealt with the issues. It's developed over time. And it's got that ability to upgrade. So you have interoperability, you have upgradability, you have backward compatibility. So it's always difficult for any new medium to come in. It doesn't matter if it's optical. And to say, can you replace it? The automotive industry has very challenging supply chains, global supply chains. So I think all those things, and obviously you and people at BMW know this as well as anyone. So I think you have to say, what is the case? What is the data rate? What is the reach that makes that required to change? So if it's simply equal, it can't displace the legacy system. I mean, my other 19th century invention is the internal combustion engine, which was built actually 1871. So eventually, technologies do shift, but it's not easy to shift them because people, like lots of people in this room, understand how to keep extending the life of the current technology. So I think that's probably the biggest hurdle, is that you've got an incumbent technology that people are used to, that a lot of people in this room have made successful, selling hundreds of millions of ports. So I think that's challenging. But again, as the data rate goes higher, as the EMC issues get there, as the power gets there, and we saw this happening with base T on the 4-pair system. Once it got much beyond 10G base T, it couldn't be competitive with what was happening on the SR side. CR is a twin-axe version, but that's reach is shrinking down to 1 meter as we go up in data rate lanes.
Okay, and we have questions. Lucas?
Yeah, thanks very much for the presentation. So I have now a lot of ideas came up, but one question for the environment testing. So you showed eye diagrams up to 125 degrees. For semiconductors vendors, we see requests coming in for 150, 175 degrees. So is that something you also experience, that the testings go into higher temperature ranges as well?
Yeah, that's a good question, and it's sort of what's the requirement in automotive and which zone are you in, right? Are you in the engine compartment? Where are you? So I think the view within CZ has been for the VCSELs, it is being tested to a higher range. For the fiber, we've talked about as low as 105 degrees C. What I can say on behalf of Corning or or ourselves as the glass suppliers, you can take it to whatever temperature you want, all the way up to 200 C. We don't see an issue there, and it's also, because this has come up in our discussions, you have to look at the lower end temperature also in terms of performance for the VCSEL at minus 40 C. But for glass, optical fiber, it's really a function of what coating you put on it and what jacketing you put on it. And then what volumes do you make that at? If you make it in sufficiently high volume, you have a cost-effective solution.
Great, thank you.
Sure.
Okay. Hey, Sam.
It's more of a comment and a question at the same time. So some of the questions that always come up when optical topic enters automotive is the temperature range of operation, which is mostly minus 40 to 125 C. 105 is the the highest in some of the applications, but also 125 should be considered. Another thing is inline connectors. So that's one thing, is when we look at cabling or any routing in the vehicle, you have to have the full solution from headers to inlines and everything. And that's some of the things that we always want to address is inlines for optical as well. And that's just one of the comments is, how mature are these connector systems with the optical fiber itself?
So, and again, first I was going to reference you, Hasim, as giving us a 100 gig use case. So we like you from that perspective a lot. The higher the data rate, the better it is for optical. Yeah, so the connectors are a challenge. It wasn't the focus of our presentation. It's not the area we're specifically looking at. But you're right, that's the ultimate link and the harness that matters. So like you're saying, that will have to go the same sort of testing. So the IEEE standard is looking at that. The ISO standard is looking at that, and it has to go through that sort of qualification to make sure it can do exactly what you're talking about. From a loss perspective, it's something, again, we can deal with in that link. We don't see that as a limitation.
And one main challenge now is serviceability.
Yep.
So right now we're addressing this with copper on automotive Ethernet because now we have engineered cabling. When you introduce optical, it's going to be a little bit more challenging as well. So that's one aspect to look at as well.
It's a very fair question. When I was in graduate school, I had a Volkswagen Beetle, and I could do everything in the car. I actually have a BMW now. I can't do many things on that car. And even the service technicians in the dealership are more limited. It's exactly what you talked about, is that as we keep adopting newer technologies, that is a challenge. I think that's true. The only thing I would say is if you look at other industries, fiber to the X, industrial, the industry learns those techniques over time. It basically adapts those. And it goes back to what Kristen said, that on the copper side, those have been worked out over many, many decades. So that is always a challenge when you introduce a new technology to a new industry.
All right, thank you.
Okay, thank you. I'm not seeing any more questions. No? Okay.
The online people are quiet today.
Okay, there is a question online, okay.
We'll be doing this later on anyway.
Okay.
Okay, so Hari Parma asks, there are many advantages of using fiber optics. As you have shown on your slides, cost is a major factor in introducing new technology. Where is the major cost breakdown? Primarily, do you see in introducing glass fiber? Is it the fiber, or is it the termination and creation of the connecting interface? Sort of very close what Haysam was asking, I guess.
It is very close to it. So I think it's more than the fiber, it's the termination of the connectorization of it becomes the challenge. But again, part of what I was trying to say is what really matters is the link cost, and that means the optoelectronics, the VCSEL source. So, and my point about data centers, that multimode is not the lowest cost fiber, but it is the lowest cost link, is really the key to this, is that if you have an optical connectorized solution, but absolutely the optical connector part and connectorization is a challenge that has to be overcome from a cost perspective.
Thanks so much. I hope that answers Hari's question.
Okay, then not seeing any more questions. Thank you very much,
Thank you,
Mabud, once
Kristen.
more for
Thank
the
you.
very interesting presentation.